This video is about limiting factors in photosynthesis, and to help explain we're going to start with an experiment. If you imagine we have a boiling tube with some pondweed in it, the pondweed is photosynthesizing because we have light falling on it from this lamp. We keep the temperature at a steady 20 degrees centigrade and the carbon dioxide concentration at 0.03%, which is about the same as what's in the atmosphere. Now imagine that at a certain time we measured the number of bubbles coming off, and we used that as a measure of the rate of photosynthesis. So more bubbles of oxygen coming off means more photosynthesis happening. So over time we increase the light intensity. So we start off with a low light intensity, measure the number of bubbles, increase the light intensity, wait for a few minutes for the plant to acclimatize to the new light intensity, then measure the bubbles again, increase and measure, increase and measure. We would eventually end up with a graph of light intensity versus rate of photosynthesis. And if we were to look at the graph, we would see that over time, as we increase the light intensity, the rate of photosynthesis increases. There will come a point, however, that no matter how much more you increase the light intensity, the rate of photosynthesis won't go any further. So for this region here, we are still increasing light intensity, but the rate of photosynthesis is not getting any higher. So for this region of the graph here, we can see that increasing light intensity does have an impact on the rate of photosynthesis. So we say that light intensity is, for this experiment, the limiting factor. We know this because if we increase the light intensity, the rate of photosynthesis will increase. So we say light is a limiting factor. Over here for this region, if we increase the light intensity, the rate of photosynthesis does not increase, so we say something other than light intensity is the limiting factor. So there's an other factor or another factor is limiting the rate of photosynthesis, and that factor is either going to be temperature or CO2. We can similarly do an experiment with increasing CO2 concentration, so we keep the temperature the same, we keep the light intensity the same this time at about 100 units, but we over time increase the CO2 concentration, and in a similar way you get a graph that goes up and flattens out. And so what you can say for this one is that CO2 is the limiting factor, and that's for this region of the graph here. And we know that because if we increase CO2 concentration, the rate of photosynthesis increases. And for the flat section here, we say, again, it's another factor that's limiting the rate of photosynthesis, and it's going to be either temperature or it's going to be light intensity. We can look at a third experiment where we keep the carbon dioxide the same and the light intensity the same, but we vary the temperature. So we carry out the experiment at different temperatures, and over time we can see that as we increase the temperature, we increase the rate of photosynthesis. It starts to level off, but what's different for this graph, which you might have just spotted a minute ago, is that rather than flattening out, the rate of photosynthesis drops rapidly, and that's because the plant actually cannot photosynthesize anymore because the enzymes that control photosynthesis have been destroyed by a high temperature. We say they have been denatured. Okay, but again for this region here, we say that temperature is the limiting factor, and for this region onwards, we say that enzymes destroyed or denatured. That's another word for enzymes being destroyed. So the plant actually would die at this point. If we go above a certain temperature, it's usually around about 35-40 degrees, although it can be higher for some plants. But if we go to high temperatures, certainly 60 degrees plus, we're going to look at the plant actually dying. So in a summary, we could look at the three graphs, and we could see that as you increase light intensity, we have this shape, same with CO2, and temperature produces this shape. It's important to remember that for this graph, CO2 and temperature must be constant. For this one, temperature and light intensity must be constant, and for this one CO2 and light must be constant. And remember, the drop here is due to enzymes being denatured, the plant actually being killed by too high a temperature. Okay, so these you must be able to recognize and remember which parts are kept constant. Now, what you might see in an exam situation is a graph that looks maybe something like this. So we're looking at, in particular, light intensity here, and if we look at the green line to start off with, we can say it's at a temperature of 20 degrees and a carbon dioxide concentration of 0.03%, and that produces a graph like so, and the maximum rate of photosynthesis flattens out at this point here. You could possibly get a reading off this graph. There might be some numbers and you'd be able to read that off, but the point here is it's at this level the rate of photosynthesis is going at its maximum possible rate. Now, if we change the conditions slightly, because we know that light is no longer the limiting factor here, something else is. Well, if we change something else, in this case I've changed the CO2 concentration, I've made it to 0.3%, which is about 10 times more, in fact exactly 10 times more than 0.03%, I can see that the rate of photosynthesis increases and it flattens out at a higher level. So increasing the CO2 concentration makes the rate of photosynthesis flatten out at a higher level, and if I then change the conditions again, kept CO2 the same as the first experiment but raised the temperature to 25 degrees, I can see that again I get a big increase in the rate of photosynthesis and it flattens out at a much higher level. So really what I can tell here is that if I have certain conditions for photosynthesis to go on, I can increase the rate of photosynthesis, and more photosynthesis equals more growth of the plant, and we can use that information for creating conditions for growing plants. What some growers do is they use a greenhouse and they can control the conditions in the greenhouse. So what they would do is use a graph like this one over here and determine what are the best factors or the best conditions for the fastest rate of photosynthesis. They might in fact also test a temperature slightly higher and have a higher CO2, and you can imagine that that would have a graph that's much higher up here, and they would use those conditions to grow plants. So we've got optimum CO2, so they increase the level of CO2, maybe increase the light intensity, and certainly increase the temperature. Okay, but you have to be careful, you have to get a fine balance. You don't want to increase the temperature too much because obviously that's going to destroy the plant. You don't want to have too high a light intensity because you know it won't actually have much of effect over a certain level, and same with CO2. So you use information like this on the graph to determine exactly what factors you'll have in your greenhouse, and that will then determine the rate of growth, and you can have a much quicker rate of growth of your plants. For example, here I've got tomatoes. Okay, and if we have tomatoes growing in these conditions with optimum levels of temperature, light intensity and CO2, they're going to grow much faster than perhaps a plant over here that's grown outside. Okay, so that's a quick overview of the use of limiting factors in photosynthesis. See you again soon.